Today, we want to start looking at vector fields, which is a new kind of function for us. We're going to have vector fields in R2 and in R3. What a vector field does is assign to each point in R2 or R3 a vector rather than just a scalar. So instead of just assigning a scalar, we're going to assign a vector. A vector field assigns a vector to each point in R2 or R3. The functions that we've dealt with before have been assigning scalars to every point in R2 or R3. And now we're assigning a vector to that point. And we got to see what the effects, first of all, we have to learn how to describe what's going on in these vector fields. And then we got to see how to do calculus on this new kind of function. So vector fields are a new kind of function for us. Before, when we had functions, I said, let's say f of xy is 3x squared times y. So to each point xy, we're just assigning a scalar. So f of 2, -1 will be 3 times 2 squared times -1 and whatever that is, -12. It's early and it's a Monday, so I might not be able to do arithmetic. Now we're going to be dealing with a function that assigns a vector. So let's say capital F at xy is, so use the example that everybody uses. Let's use the example that everybody uses first. Minus y times I plus x times j. So now the input is still a point, but the output is this vector. So now if we evaluate f, this capital F at 2, -1, we'll have minus y times I, so 1i, plus x times j, plus 2j. So the output is a vector rather than a scalar. One of the things that we might be doing is thinking of the inputs for our vector fields as vectors as well. So we might say, we might write f at r so we might use vectors as inputs. Any questions? All right. Taking a look at this example, f at xy is minus yi plus x times j. If we start evaluating this vector field at a bunch of different points. So just like before, we can evaluate the vector field at the function at a bunch of different points, x and y. So at the point, let's say 0, 0, we get the 0 vector, 0i plus 0j. At 1, 1, let's go with 1, 0, traditional style. We'll have negative y, so 0i plus 1 times j. So if we go over and try to plot this vector field, at the point 1, 0, we draw the vector 0, 1. If we go to the point 1, 1, at the point 1, 1, where this last vector ended, we'll have minus y, I, so minus 1 times I, plus 1 times j. So at that point, we'll have the vector negative 1, 1. So that vector will go negative 1, 1. At that point, we see this vector. At the point 0, 1, we'll get minus y, so minus 1 times I, plus x times j, so plus 0 times j. So at the point 0, 1, we get the direction vector negative 1, the vector negative 1i plus 0j. Now, if we plot, say, at 2, 0, just going a little further out, we'll have 0i plus 2j. So at this point, we'll have a longer vector. So f at 1, 1, at the point 1, 1, the vector is negative 1i, so that's negative 1 in the x direction, that's to the left, and 1 in the j direction. So we're not plotting the vector 1, 1, we're plotting the vector negative 1, 1. So here are the vectors. At these points, we plot these vectors. So at these points, we plot those vectors. So we're not plotting the vector 1, 1, we're plotting the vector negative 1, 1. If we look at vectors on the other side, let's see. So if I plot the vector 2, 2, if I find the vector, evaluate the vector field at 2, 2, we'll get a negative 2i plus 2j. So that vector at the point 2, 2 will go negative 2i plus 2j. If we look at vectors on the negative side, so if I plot the vector at negative 1, 0, so at the point negative 1, 0, I'll get 0 in the I direction, -1 in the j direction. So we can see that plotting vector fields by hand especially is going to be much more difficult than plotting, say, a function of one variable. Because for a function of one variable, we just need to plot a height. But now at each point, we're not just having a magnitude, we're having a direction as well. And so this graph could get very messy very quickly. And also, if I'm going to have a machine do this, I'm going to have to tell it how often it's going to plot values, because I can't just have it draw everything, because a lot of these vectors are going to overlap. So we can see that these vectors, as x increases, everything along the x-axis, since every point on the x-axis has a y-coordinate of 0, all the vectors along the x-axis are going to be vertical, because if y is 0, there's no I component. Similarly, all the vectors along the y-axis are going to be horizontal, because along the y-axis, x is equal to 0. And so we'll have no j component in our output. But at each point, we are assigning a vector. Now, this raises the question, can we have a machine plot vector fields for us? And we shouldn't be surprised when I click over to Wolfram Alpha and I'm like, well, hey, Wolfram Alpha, can you plot a vector field for me? And it's like, sure. So here's the, is this the same vector field? Yeah. So here are all the things that I have to tell the vector field to plot. First of all, I have to list the vector field, and we just listed it in curly brackets for Wolfram Alpha. Wolfram Alpha wants its vectors in curly brackets. And I say the first component is a negative y, and the second component is an x. And then you have to just tell it what your lower and upper limits for x are and your lower and upper limits for y. And so here's the vector field that we're looking at. Now, this is over a wide range. This is going from -10 to 10. We can cut these down. To look at a different section of the plot. And it's going to look the same all the way down. So when we're plotting a vector field, notice that near 0, near the origin, we've got these little small vectors. So the size of the arrow is going to indicate the magnitude of the vector. So we see as we move along the x-axis, the vectors that are crossing the x-axis are getting bigger. Notice also that they're all vertical, because along the x-axis, the y component is equal to 0. And so for this particular vector, the first component is -y. And if y is always 0, then our vectors along the x-axis are always vertical. The other thing that we'll want to notice about this vector field is the flow through the vector field. If we pick a point and start following it around, if we start here at this point 2, 0, we're going vertically upward. But the more we go up, the more y component, the y component becomes important. So that starts pulling us to the left. So we can see the arrows kind of pointing along this curved line. And when we pass, we're going purely horizontal when we hit the y-axis. And then the x, then when the x's drop negative, our direction starts pointing negative. And so our flow around this vector field is going in circles. And this is the usual first example in all calculus books for vector fields. Welcome to tradition. Now, this raises the question, how are we going to do this with three-dimensional vector fields? What if we have a vector field that has an output that is in R3? So once again, the internet has us. Here's a vector, GeoGebra has a vector field plotter. And the cool thing about the 3D vector field is that you can move it around. This is a very simple vector field where the x coordinate is 1 and the y and z coordinates are 0. So all these vectors are just going in the x direction. But if we want them to go in the y direction, we can change the q to go, let's say 1. And now they're all pointing at this 45-degree angle. But notice that if we look at it with z going up and down, they're all moving flat because I have no motion in the z-axis. If I change motion in the z-axis to -1, now they're all pointing down. And now the vectors are stuck in the bottom because we have brutal boundaries in GeoGebra. It will not, absolutely not show anything below the floor. So we have a new kind of function. Our inputs are going to be points in R2 or R3, and our outputs are going to be vectors. We got to think about what we could possibly use this for, because that's always what people ask. If we just had a whole day where it's like, today we're going to talk about 3 + 4, and then spent an hour talking about that 3 + 4 is 7, and then tomorrow we'll move on to 3 + 5. Typically, we don't ask a lot about when am I going to need to do this. Partially because it's obvious. We have to add and subtract to do things like balance our checkbook. No one does that anymore, but we have to manage our finances. We need addition and subtraction. But the question about when am I ever going to need this is not really the question. Otherwise, when you start doing the easy level of algebra, 3x + 2x is 5x. No one asks, what's this x business all about? Because you're like, well, just add the numbers in front, and everyone's like, oh, okay, it's easy enough that no one bothers to ask, so, oh, well, what's the point of all this? It's when the math starts getting hard that people start saying, hang on, why do I have to know this? This looks like it's going to require effort. Therefore, I need some more justification. You know what I mean? Then the tricky part is that we try to teach this to teenagers. And that's typically when human beings start to say, look at authority and say, no. And we just got algebra out of the way when they were still little kids, and they were just like, I'll do this. And the kid would be like, all right. I think we'd have much higher success rates in algebra. So what are we talking about? Oh yeah, vector fields. So we've got this new kind of function. We want to think about what the outputs look like vectors. And then the other thing that we want to think about is that what is the flow of the vector field? So at each point we have a vector assigning a direction. Imagine the flow of the vector field as the wind, or imagine the vector field as the direction that the wind is blowing. And so then we can imagine the flow of the vector field as a leaf on the wind. Just imagine a leaf on the wind and watch how it soars. At each point, the vector field is telling you what direction the leaf will be going. As the leaf moves, we have to reevaluate the vector field to find out what direction the leaf is going at that point. So at the point 1, 0, the leaf is moving vertically. So it moves up a little bit, but as soon as it moves up a little bit, let's say 0.1 later, it's going to start moving to the left because now the y coordinate is positive and we'll have minus y times I becomes a term. And so we start moving to the left. And as soon as it moves to the left, it's moving less up. So as the leaf moves around, we have to continually reevaluate which direction the leaf is going. So we want to imagine the flow of the vector field. We want to think of the vector field as the wind and imagine what would happen to a leaf on the wind. Any questions? All right. Less talking for the big thing that we're introducing today, vector fields. Vector fields are everywhere. So whenever you walk into the room, look for the vents that are going to be blowing air into the room and imagine what the vector field should look like in the rest of the room because of that vent. All the air pushing out of that and how the air spreads out. When you're driving in your car and you turn the vents on, think of that's another place that you can start imagining the vector fields and you can see how it flows. Right near the vents, you'll see some long vectors because the air is coming out very fast, but it's harder to feel it farther along because the vectors are getting smaller. I guess in those examples, we have a lot less wind. So instead of a leaf, just like a little dust particle, imagine that flying around. All right, that's it for today. Think about vector fields, start seeing vectors everywhere. That's it for today. I'll see you all on tomorrow. Everybody have a good day and thanks for playing.